everyone. My name is Abhi. I'm going to give a talk on Introduction to Ring Theory. So okay, before we get to the complicated stuff, let's talk about something everyone knows about. Integers. Like everyone here knows about integers. We'll look at certain properties in integers, right? Which are commonly known. So you can add integers. You can take 2 and 3, you can add them, you get 5. You can multiply integers. Again, 2 into 5, 10, yeah. Subtraction is just adding an inverse, right? Adding the negative of a number. That's just subtraction. So we won't write it as a separate operation. Then we have division. We won't look into division right now. It's a bit more complicated. So we're concerned with addition and multiplication. So yeah, we have integers are closed under addition and multiplication. What that means is, if you take 2 integers and add them, you get another integer, right? And then if they're it's closed under multiplication. If you take 2 integers, multiply them, you get another integer, right? That's called the closure property. So it's like closed in that set. Then we have something called commutativity, which basically means if you take your order of operations does not matter. So if you do 2 into 3, it's the same as 3 into 2. All of this may seem obvious, but we'll look at examples in further where this is not true, right? So commutative, even addition is commutative and multiplication is commutative. Then we have the distributive law, which is 3 into 2 plus 5 is 3 into 2 plus 3 into 5, right? This is called the distributive law. Distributivity of addition over multiplication. Then we have 2 special numbers in integers. And the only 2 special numbers. We have 0. What's special about 0 is you can take any number, add 0 to it, you get the same number back. That's why it's called the additive identity, because you can add any number to 0, you get the same number. And now that you have an additive identity, you can define an inverse. What an inverse is basically, if you take 5, what do you add to this such that you get 0, right? That's negative 5 in this case, right? So you get 5 minus 5 is 0. 5 plus negative 5 is 0. So let's say negative 2 is the inverse of 2. So those are additive inverses, they're called. Then we have a multiplicative identity, which means you take a number, multiply it by 1, you get the same number again. Again, here you don't have multiplicative inverses, right? If you take 2, you have to get 1, you have to multiply it with 1 by 2. But 1 by 2 is not an integer, right? So you don't have multiplicative inverses here, but you have a multiplicative identity. So we look at another example next. It's called Z mod, Z by N, Z mod N Z it's called. The name, it may seem weird right now, it will make much more sense in a future talk, but just keep the name in the back of your mind. What's important is, it's like maths of remainders, or it's called clock arithmetic. So basically how you work with it is, imagine a clock, right? You have 12, 1, 2, 3, 4. Right, you have a clock. There are only 12 numbers on the clock. So in your 24-hour clock, how do you show what is 13 o'clock? Yeah, what is 17? Fine. So how do you do that basically? How do you take 17 and get 5? Yeah, how do you get it like that? Yeah, it's like that, right? Or 5 is, in other words, 5 is the remainder when you divide 17 by 12, right? So if you Now, this is not in the 24-hour clock. Let's say 29 o'clock. What would that be? Yeah, it will be 5 o'clock, right? How did you do it? You found the remainder, right? So that's basically what Z mod and Z is, right? You are thinking in terms of a clock. Now, what N is over there is, in this case, we took N to be 12. So there were like 12 numbers. Oh, and commonly, this is not called 12. This is called 0, because when you divide 12 by 12, you get the remainder as 0. So it's called 0. So generally, in a clock there are 12, but there can be any number of elements. It can be any number. Let's take Z mod 5Z, right? Again, the name is not very relevant now, but try to guess what is there in this. Yeah, it's 0, 1, 2, 3, 4. So now you might ask, what about some larger number? Let's say 72, right? What would you put in here? Yeah, you put 0 to 71. You get it, right? Because remainders are from. Now let's say Z mod 5Z. Say, take a random number, 52. What would 52 be in here, actually? It's as I told, it's the remainders, right? Yeah, it would be 2. So again, it's a remainder. So you can take the entire all the integers and boil them down to 0, 1, 2, and 2, 3, and 4, right? So I'll give some more examples. What do you think 67 is over here? 2. 75. Yeah. So it's basically you take a number, get the remainder, and see where it is, right? So this is Z mod 5Z. If you have Z, you can have Z mod 6Z, Z mod any number Z, right? This leads to something called modular arithmetic, right? Okay, so now we will see, just like we saw in integers, we'll see the properties. Addition. You can take 2 elements, right, and add them. Let's say over here, you take 2 and 3. What do you get when you add them normally? What is 5 in this set? 0. So you take 2 and 3. When you add 2 and 3, you get 0. Okay? In this set. Right? Now, let's take another example. 4 and 3. What happens when you add 4 and 3? Oh, yeah, you get 2. Why? Because 4 plus 3 is 7. 7, the remainder is 5. By 5 is 2. Right? So that's how you add. So let's do this. Let's take for 12. You add 11 and 7. What do you get? It's 6. Because 11 plus 7 is 18. The remainder when you take 18 and 12, it's 6. Right? So yeah, I told the example of 12. Okay, so the next thing, you can multiply 2 things. What do you think is the answer when you take 3 into 4? Try taking again. Yeah, it's 2. 3 4s are 12. You see what corresponds to 12? It's 2. So 3 into 4 is 2. I'll give another set. Let's say Z mod 6Z. Right, this is 0, 1, 2, 3, 4, and 5. What do you multiply 2 and 3 here? What do you get? 0. Okay, so now keep that in the back of your mind. Closure property. We saw closure property, right? You saw that whatever you do, it comes back to the set. Multiplication and addition. It's commutative. You can see that. Like 3 into 2 and 2 into 3 were the same things. It follows distributive law. You can take 3 into 4 plus 2, it's the same as 3 into 4 plus 3 into 2, whatever, it's the same. There's an additive identity, which is 0. So, in in other words, in this case, even 6 is an additive identity. Even 12 is 18. Any multiple of 6 is an additive identity, right? They have a multiplicative identity, which is 1, right? You get why 1 is a multiplicative identity. So 7 is also a multiplicative identity in this case. And multiple plus 1. Yeah. So another interesting thing is, I have written AB equals 0. So in integers, it was kind of assumed when you have like two numbers and you multiply them to get 0, one of them has to be 0, right? That was kind of our assumption and we've always believed it. But in this set, Z mod and Z, we saw you took 2 and 3, you multiplied 2 and 3, you got 0. So 2 is not 0 and 3 is not 0. But when you multiply them, you get 0, right? We'll give a name to such things later, but just keep this in the back of your mind, right? So we'll look at another example now. Okay, Z of x. Now Z of x, right? It's called Z adjoint x, and in most cases, like always, Z is bold. Since you can't write bold in actual things, you give it like an extra dash. So this is called Z adjoint x or Z of x. What this means is, you all know polynomials, right? So polynomials are something like 3x squared plus 5x plus 2. If the coefficients are integers, right? It's called, it is a part of Z of x. So it's basically polynomials with integer coefficients, Z of x. An example is something like x cubed plus 5x squared plus 3. Some random polynomial which you can think of. It's an example for this, right? But you can't have something like 1 by 3 here, because 1 by 3 is not an integer. Just remember, all of these are just number systems in one sense, right? You saw the previous thing, that was a number system, right? Integers is a number system. Even this is a number system. It's just you have an x over here, right? So you can add two polynomials. You can multiply two polynomials. You can see that when you add two polynomials, it is another polynomial. These are stuff you can actually prove. Like some of these you can actually prove. You don't have to believe me. It's commutative and distributive law is there. Then the additive in identity is 0, right? Or the 0 polynomial in this case, right? Multiplicative identity is 1. And over here, unlike the previous case, AB equals 0 means A is 0 and B is 0. In fact, like whenever you solve your quadratic equations, you get something like x minus 2 and x minus 3 equals 0. You always use this fact that either one of this has to be 0, and then you write x equal to 2, x equal to, or x equal to 3. You always put an or over there, right? Because one of this has to be 0, right? So we are done with Z of x, right? Now, instead of x, we'll put in some values we know over here. Okay, so next slide, Risha. We'll put in I. I is basically square root of -1. Basically, when people were solving quadratic equations, they realized that some quadratic equations didn't have solutions. That's because there's something called the quadratic formula. Under the root, you got a negative. And in normal sense, in integers and stuff, you don't know what root of a negative number is. So they started calling root of -1 I. So root of -4, say, is just 2i. It's just 2i. Okay. Similarly, root of -9 is 3i. Right. So basically, this is I. Right. So you put I instead of x. So what do you get? Polynomials with x. So it'll be something like we had x cubed plus 5x squared plus 5, right? Plus x plus 5. x plus 5. Now we'll put I over here instead of x. You get I cubed plus 5i squared plus I plus 5. Right? Now since you get I cubed, I squared and I. But you realize that I squared, I cubed and all can be simplified. Let's look at this. This is I part 1, root of negative 1. I squared is just root of negative 1 whole squared, which is negative 1. I cubed is I squared into I, which is your laws of indices, right? The I squared is negative 1, so you just get negative I. I part 4 is just I cubed into I, right? What is I cubed? Negative I. Okay, yeah, you can take it as I squared whole squared. What is I squared? Negative 1, right? So this is just negative 1 whole squared, which is just 1. Then you take I part 5. This is just I into I part 4, right? I into 1, which is I again. You take I part 6, which is I into I part 5. So I into I. So it's negative 1. You realize that this is I part 1 is just I squared is negative 1, but I part 5 is I. It's going to repeat on and on. So what you have to do essentially to find any power of 5 is, let's say you're given something random, I part 76. You look at I part 76, find its remainder when you divide it by 4, right? In this case, it's 0 or 4, right? Like 0 is 4 in this case. So you take I part 4, so it's 1. So something random like I part 27. It is, what's the remainder when you divide 27? It's 3. So it's I cubed. So this is just negative I. It's 3. Yeah, it's 3. So that way you can find any power of 5. Now, you see over here that you get negative I cubed is negative I squared is negative 5. This is I. You get I plus 5. This was a horrible example because you get 0. But in general, you get a number which is of the form a plus b. Because you see, all of these turn into I, negative 1, negative y or 1. Like any power you have, like x bar, some random number, you get something in terms of I, negative y and sum. So you can take all the I terms and add them. Take all the non-I terms and add them. You ultimately end up getting something of the form a plus bi, right? Where a and b are integers. The symbol is called belongs to, when a comma b belongs to integers. It's the Greek letter epsilon. So basically z of I is all numbers of this form, right? So 3 plus 2i, 5 plus 6i, all those are a part of z of I. Now again, all of these things are true in z of I, right? Even ab equals 0 means either a is 0 or b is 0. Yeah, that's true. Okay. So next, we're not done with that. We have z of root g. Okay. So again, remember this was the z of x. So and we put in I. Now let's take z of root d, right? Like, okay, root d over here is just, d is some integer which is not a perfect square. Like 7, 8, it's not a perfect square. So let's take an example, z of root 2. Z of root 2, right? What this is again, you take a polynomial and instead of x you put in root 2, right? So x cubed plus 3x squared plus 7x plus 3, whatever. Okay, it's a random polynomial. It can be of any degree, anything. you plug in root 2 here. Root 2 cube 3 into root 2 square plus 7 root 2 plus 3. Okay, what is root 2 square? 2. What is root 2 cube? 2 root 2. Okay, so this is just 2 root 2 and then there's a 7 root 2, so it's a 9 root 2, right? This is root 2, it's 3 into 2, 6 plus 3, 9. So this is 9 plus 9 root 2. So ultimately, whatever, you saw how root 2 cube became 2 root 2. So root 2 power 5 will just become something into root 2. So everything will become root 2 into something plus something, right? So again, just like how we saw in I, z of root t, let's take root 2 right now is a plus b root 2 for all a comma b, which are integers. If you can't see this, it's when a comma b are integers. Again, belongs to integers. So now we can define this for any number. It need not be 2. Not any number, any square free integer. It can be 3, it can be 4. Sidecar can't be 4. My bad. In fact, it can be -1. What do you get if you put it? You get z of I again, right? So you see that's just a generalization of this, and all of this is a generalization of z of x. So from a single number system, you can call it, you get like 3 or 4 more. In fact, root d, you can have anything. You get a lot more number systems. In fact, you can define z of root 2 comma root 3, right, and write it as a root 2 plus b root 3 plus c root 6. Right? Okay, anyway, coming back to this, you have z root d. You can see all of these are true. I'm not going to go through all of it again. So now the next thing, again, we're back to familiar territory. Rational numbers. What are rational numbers? Yeah, okay. P by Q, where P and Q are integers, Q is not 0. Yeah. Can you add rational numbers? You can multiply rational numbers. Are they close? When you multiply two things, is it commutative? Yeah. Okay, then is distributive law followed? Yeah. Is there a 0? Is there a 1? Yes. All of it is true. And AB equals 0 means A or B is 0. But now we have an extra thing, right? Remember in integers when I told 2 into half is 1, so you don't have multiplicative inverses in integers, but because half is not an integer. But over here you do have a multiplicative inverse for everything, right? So let's say 5 by 7. What is the multiplicative inverse? 7 by 5. So every non-zero element, you can't take 1 by 0. Every non-zero element has an inverse. Okay? What's an inverse? You multiply it, you get your identity, which is 1. Okay, so we are done with rational numbers. Now, this is it's interesting. It's weird, it's interesting. Quaternions are basically, they're like generalizations of complex numbers, or not complex numbers. It's z of I, but it can be any real number, but it's more generalized. So what you do is, I'll write the definition first, then explain it. So its symbol is this because it was discovered by a guy called Hamilton. So it's Hamilton's quaternions. It is all numbers of the form a plus bi plus cj plus dk, where a, b, c, d are real numbers. Okay, the real numbers. Now, this looks complicated. So wait, before that let's define I square. Yeah, what I, j, k are. I square, j square, k square are all -1, or roots of negative. Yeah, they're -1. But the thing is, IJK have this like directionality towards them. You might say they're equal, you can just add stuff. They're not equal. They have like a direction to them. It's similar to vectors, not exactly vectors, right? It's not vectors over here, but it's basically Hamilton is the guy who invented the vector notation and this. So he gave both of them I, J, K. So it's not the exact same thing, but they are similar, right? And then an interesting thing, just like we learned cross product in vector, right? So over here, Ij is K, right? It's similar to cross product. Jk is I, Jk is I, and Ki is J. Yeah. But the thing is, Ji is negative K. It's not K. So remember in all those things, when we were like, yeah, it's commutative. Over here only addition is commutative. Multiplication is not commutative because Ij is different from Ji, right? So yeah, again we can see all of these things are true. 0 is an additive identity. If you put B, C, D and A as 0, you get your additive identity. If you put B, C, D as 0 and A as 1, you get your multiplicative identity. And it is in fact AB equals 0 means A is 0 or B is 0. That is true. And again, every non-zero number has an inverse. The inverse over here is not very intuitive, like rational numbers inverse. I'll just give the inverse, right? It's the inverse of this. This is a symbol for, and when I'm talking about inverse, I'm always talking about multiplicative inverse because everything has an additive inverse. In general, from now, if I'm talking about identity, it's the multiplicative identity. If I'm talking about inverse, it's the multiplicative inverse. So, yeah, the inverse of this is just A minus Bi minus Cj minus Dk by A squared plus B squared. Now, you can try later. You know these rules, right? You can try multiplying this and this and check if it's actually 1. It's really cool to do that. It's basically a distributive law, right? You just like expand, you get A squared plus B squared plus C squared plus D squared in the numerator. Everything cancels. So now, next. Yeah, so basically there's this story, right? Okay, there's this problem. It's called Fermat's last theorem. It was given by Fermat, an extremely famous guy. There's an entire story about how this theorem came about. He wrote it in the margin of his book and told I have a proof and then died. Okay. So yeah, that's Fermat's last theorem. So for the longest time ever, until like 2000 something, for like 400 or 200 years, no one found an answer to that problem. Okay. It was a really hard problem, and even though it's been solved now, it's considered hard because it had the most wrong proofs ever. Like people were thinking they solved it, but there was some assumption they took which is not true. Now there's this guy Lame. His name is Lame. Yeah, he came and gave another wrong proof, but it looked incredibly true. Okay, his proof. I won't show his proof here, but in fact, he will do it, Rishan. Okay, yeah, fine. He'll give the right proof. Whatever. So Lame gave a wrong proof, and then a guy called Kamal, he came and told that the proof is wrong because of this extremely weird assumption that Lame did. So then, because of this, Kamal created algebraic number theory. What we are learning today. Ring theory, algebraic number theory. All of this was created because Lame had made a mistake in this problem, right? We'll look at what was wrong with Lame's proof at the end, and the actual proof we'll look at it in the next session. So we'll go to the next thing. Okay, so now definition of ring. You remember all those number systems we looked at, right? Now the thing is, we take all of those and just define it as a ring. So it's closed. Addition is commutative. Multiplication need not be commutative, as we saw here. There are two operations: addition, multiplication. Multiplication is associative. What that means is A into B into C is A into B into C. In fact, there are places where even this is not true, right? But in rings it is true. Distributive law holds. Again, what's that's distributive. There's a multiplicative identity, there's an additive identity. Multiplicative inverses need not exist, like integers, but additive inverses always exist. In fact, the commutativity of addition, right? It you don't need to assume it. You can prove it using your distributive law. How that's done is, and remember, in this entire session, we'll have only these things to work with. Like we know, like no other thing, except for some proofs. Okay. So now, consider 1 plus 1 into A plus B. We can distribute this in two different ways. Okay? 1 into A, right? 1 into A plus B plus 1 into A plus B. Right? You get 1A plus 1B plus 1A plus 1B. You can check that it's not, we have not assumed it, but 1 into A is always A. Right? But that's easy enough and it's intuitive. You get A plus B plus A plus B. Okay? Now on the other side, we'll take 1 plus 1 into A plus B again. These are equal. So now you get, we'll distribute it like this. 1 plus 1 into A plus 1 plus 1 into B. Now you get 1A plus 1A plus 1B plus 1B. So basically you get A plus A plus B plus B. Now plus B plus B. Now you don't know these two things are equal. It's not cancel them. But you know A is equal to A. So basically what does cancelling mean? You're adding the inverses to both sides. Inverse of A, you're subtracting A basically. You cancel A, you cancel B. You get B plus A equals A plus B. Okay? So now, yeah, that's done. The next thing, what? Okay, what we would want in the definition? Yeah, we would want multiplication to be commutative in integers, but it's not there in the definition. And we would want multiplicative inverses to exist. Okay, before we look at that, we'll look at this thing which you've been taught since 4th, 5th, whatever, that negative into negative is positive, right? You've always learned that. It's not intuitive that it's true, right? Why should two negative numbers multiply to get a positive number? It turns out you can in fact prove it using distributive law. Okay? That's the same as doing negative 1 squared is 1, negative 1 into negative 1 is 1. We'll prove that right now. Take negative 1 squared, right? And add negative 1. Okay? So now, by distributive law, right? You can factor out negative 1. You get negative 1 into negative 1 plus 1. You're factoring out negative 1. So you get negative 1 into 0, which is 0. So now, you see that negative 1 squared plus negative 1 is 0. Now, if you add 1 to both sides, or basically move the negative 1 to the other side, you get negative 1 squared plus negative 1 is 0. You see that negative 1 squared equals 1. So that's a proof for why negative into negative is positive. Now let's look at different types of rings. Okay, we have commutative rings. right, where multiplication is commutative. We have something called integral domains. As it's there in the name, it's like integers, wherein you have it is commutative, right? As you can see with that graph, not the graph, the diagram. But there's a thing that AB equals 0 means A is 0 or B is 0. As we saw, there were some examples where that was not true, Z mod and Z. So AB equals 0 means A is 0 or B is 0 in integral domains. Then we have something called division rings, right? Wherein every non-zero number has a multiplicative inverse, right? We saw several examples. Then we have fields, where it's an integral domain, okay? As you can see in that chart, it's an integral domain, but it's also a division ring. So you can try guessing. What do you think? Give an example for a commutative ring. Again, ring is just a name. What is? It has to be commutative. Integers. Natural numbers is not a ring. Whole numbers is not a ring, because there are no additive inverses. Yeah, integers. It's a commutative ring. Integral domains, an example. Where AB is, no, it's simple. Where AB is 0 means A is 0 or B is 0. No, that's not an integral domain. Integers again, right? In fact, it's there in the name, integral domains. Okay? Okay, yeah, I showed you, right? You saw in Z mod 6Z. You got 2 into 3 is 0. Right? What definition of integral domains means is that it's there that A into B is 0 means either A is 0 or B is 0. But over here, neither A is 0 neither A is 0 nor B is 0. Right? So Z mod 6Z is not an integral domain. In general, Z mod NZ is not an integral domain if n is composite. If it is n is prime, it turns out to be an integral domain. I have written that there, but it turns out to be field. I won't prove that today. Try guessing an example for a division ring. Yeah. Any other example? Or what's the last example you saw? Like not over here, before the story. Quaternions. That's an example, right? For a division ring. Fields are commutative division rings. So what's an example? Integers, it's not a field. 2 does not have an inverse. Real numbers is an example of a field, because every number has an inverse, right? Now we'll go to the next thing. Okay, units of a ring. So basically, what do you think of when you think of a unit? Yeah, everyone thinks of 1. I hope. Yeah. So what's special about 1? It divides every other number, right? Any number by 1, you get the same number. It divides every other number, right? In fact, even negative 1, right? Negative 1 divides all other numbers in the integers, right? So such numbers are called units. A more formal definition is not a formal definition. It is a definition. UV equals, if there are 2 elements, U and V in the ring. If U into V is 1 for some integer, for some element V, it's called a unit. Okay. So you can see why, and also in general, if there's a ring R, right, the set of units is denoted by R superscript X. So now you have in integers, the units are 1 and negative 1. You get why, because you can multiply, there's a number with which you can multiply 1 to get 1, which is 1 itself. You can multiply negative 1 with negative 1 to get 1. So both of them are units. There is no number in integers which you can multiply with 2 to get 1, right? 2 into half is 1, but half is not an integer, right? So before we look at the other example, try to guess what's a unit in rational numbers. What's a unit, right? Yeah, you're thinking along the right lines. One is a unit, some other units. Think. Yeah, all of them are units except one number. Yeah, except 0, everything is a unit. Because you can take any rational number, multiply it with something to get 1. So, in rational numbers, every single number is a unit. In integers, it's -1 and 1. In z of I, the units turn out to be 1, -1, I and -I. Yeah, I can prove that. Okay, so again, let's go back to the definition. What does it mean for something to be a unit? Let's take two numbers, two non-complex numbers which are of the form a plus bi, right? So let's say z equal to a plus bi, w equal to, and such that z into w equals 1. You see, this is the definition of a unit, right? Z into w equals 1. That means z is a unit, right? So what does this mean? Yeah, z into w is a unit. So w is 1 by z. Okay. What does this mean? W equals 1 by a plus bi. Now you can multiply the top and the bottom with a minus bi, right? Again, I is root of -1 here. So I'll continue my things here. You get a minus bi in the top, a minus bi into 1 is a minus. If you multiply a plus b and a minus bi, it is of the form x plus y, x minus y. So you get x squared minus y squared, right? But so it's a squared minus bi squared. I squared is -1. So it becomes a squared plus b squared. So you get a squared plus b squared. You get w has to be this. Now, again, writing it in the x plus yi form, right? W equal to a by a squared plus b squared minus b by a squared plus b squared into I. Now this is interesting, right? So you have w is a part of the set, part of z of I, right? So this entire thing has to be a part of z of I, right? What does that mean? This has to be an integer and this has to be an integer, right? So now what that means is, how can this be an integer when a is a multiple of a squared plus b squared, right? When b is a multiple of a squared plus b squared, these two things can be integers. So what does this mean? It means a squared plus b squared divides a. In fact, it divides mod of a because a can be negative, right? Mod of a means you just take out the negative side from a, and also a squared plus b squared divides b from this. Now, can a multiple of a number, I'm talking about positive here, because a squared is positive, b squared is positive, mod of a is positive. Can a multiple of a number ever be greater than the number? Can a multiple of a number be greater than the number? Sorry, my bad. Can the number be greater than the multiple? No, right? It can be equal. 2 into 1 is 2. So, it can be greater when, it can be less when it's 0. 2 into 0 is 0. Except for that, everything. So, you get a squared plus b squared is less than or equal to a, right? And similarly, you get a squared plus b squared is less than or equal to b. Now over here, put b as 0, what do you get? A squared is less than or equal to a. Okay, over there if you put b as 0. Now, how can when can a squared be less than or equal to a? Try thinking. 1, 1, 0, 1 more. 0, 1, 0, negative 1. So this means a is 0 or plus or minus 1, right? Similarly, over here, where is it? This. You put a as 0 over there. You get b squared is less than or equal to 1b. Where can this be true? 0, 1, negative 1. Again, same thing. So b is 0, 1 or negative 1. Right? So now, what are a and b? They're just this, right? So you put in all those values. You have 0, plus or minus 1, right? You get z is. It can be 1 when you put a as 1 and b as 0. It can be negative 1 when you put a as negative 1 and b as 0. It can be I when you put a as 0 and b as 1. It can be negative I when you put a as 0 and b as negative 1. These are the only possible things, right? So z can only be these things. And what did we take z to be? Z was just a unit, right? We defined our operation in such a way. So these are all the units you have in zi of x. Now, similarly in z mod 12z, you can have units. Before that, now you know the definition of a unit, right? Try finding, before that, try finding units in z mod 6z. Right? What is z mod 6z? Oh, 5. Try finding units. Basically, what you do to find units is you take a random number, see if there's some number with which you can multiply it to get 1. Okay, so 2 into 3 is not 1. 0. 1 into 1. Yeah, 1 is a unit. That's right. So 1 is one of the units. Think of some other units.
5 into 5.
Yeah, what is 5 into 5? What is 25 in this? 1. You get that 5 into 5 is 1. Hence 5 is a unit. So you get 1 and 5. It turns out you can check for 2, 3 and 4. Only 1 and 5 are the only units over here. So you get why 2, 3 and 4 can't be units. I mean, an observation is, you know what LCM GCD is, right? So the GCD of 2 and 6 is not 1. GCD of 3 and 6 is not 1. GCD of 4 and 6 is not 1. Just keep that in the back of your mind. But GCD of 1 and 6 is 1. GCD of 5 and 6 is 1. Right? So now, coming back to Z mod 12Z, your clock, right? Over there the units are 1, 5, 7 and 11. You see why? Because 5 into 5 is 25. What's that? What's 25? 1. 1. Yeah, it's 1. In this set it's 1. What's 7? 7 into 7. 49 is 1. And note, here it turns out that they're equal. Like it's always 7 into 7. But that may not always be the case. Even 11 into 11, 121, that's 1. Right? So you get all the units over there. It turns out the rest of the things are not units. I wrote the fact down. If M is a unit, it means GCD of M and N, this is N, is 1. And we proved this. I won't prove this today. Prove that if U is a unit, even negative U is a unit. It's actually a simple proof. You take U, right? You have some numbers U inverse. Let's call it V. U into V is 1. This is the definition of a unit. Now you can multiply with 1 on both sides. But what is 1? It's negative 1 into negative 1. Right? So you can take U into negative 1 into negative 1 into V equals 1. But remember that multiplication is associative. So you can combine this. You get negative U into negative V is equal to 1. That means negative U into something is 1. That's our definition of a unit. So if U is a unit, negative U has to be a unit. You can see that over here. 1 is a unit, even negative 1 is a unit. I is a unit. Negative I is also a unit. Right? So we are done with units. Let's go to the next thing. These are zero divisors. Remember when I gave you the example 2 into 3 is 0 in Z mod and Z. In such a case, 2 and 3 are called zero divisors. What do you think are the zero divisors in this? 2, 3. Yeah. Then anything else? Yeah. So 6 is 0 again. So you get 2, 3, 4 are zero divisors. And 0 itself is not a zero divisor because in the definition of a zero divisor, A is not 0 and B is not 0 is given. So in Z mod 12Z, there's one number missing here, that's 9. But you see why, how do you get 2 to be a divisor, a zero divisor? In Z mod 12Z. 2 into 6 is 0. 3 into 4 is 0. 4 into 3 is 0. Right? 8 into 3 is 0. 6 into what is 0? Yes, 6 into 10 is 0. Because 6 into 2 is also 0. Yeah. Yeah, so all of these, what about 9? 9 into 4 is 0. 9 4 is 36. 36 is a multiple of 12. So, skip 9. Let me think. Okay, so you get all of these. Now you realize 2, 3, 4, 6, 8, 9 and 10. If you take the GCD with 12, it's not 1. Right? Like GCD of 2 and 12 is 2, not 1. So, in general, in Z mod and Z, if M is a zero divisor, it means Z mod and Z. In Z mod and Z, it's true only if GCD of M comma N is not equal to 1. It turns out all the numbers in Z mod and Z, it's either a unit, a zero divisor or 0. There are only 3 possibilities. And a zero, in a general ring, a zero divisor can never be a unit. We can prove that, but I won't do it now. Next. Okay, we've already looked at this. What does A divides B mean? It means A equal to AC for some C, right? That's the definition of A divides B. It works like this in integers. So now next thing. We have primes. How are primes defined in integers? They have only 2 factors, 1 and a more good definition is it means prime divides AB in integers means prime divides A or prime divides B for any A and B. Okay? Now you look at a number like 4, right? So let's say 4 divides 6 into 40. I find 2. 6 into 2. 6 does divide 12, right? I mean, sorry, 4 does divide 12, right? But does 4 divide 6 and 4 divide 12? 4 divide 2. Does 4 divide 6? No. Does 4 divide 2? No. 2 divides 4. 4 does not divide 2. Okay?